Okay, so we're going to look at a really exciting application of integrals. We're going to look at how to use integrals to find volume and volume by slicing. So what I want to do is, think about these two volumes that we know. The first one, is a box. So we've got width and length and height. The next one is a cylinder. So we've got a little bit of radius and some height, delta x. So we know that the volume of a cylinder is pi r squared h, which in this case is pi r squared times delta x. But let's think about where that comes from. So, and this is a important precursor to today's lesson. So if we think about there being a little kind of a cutout, so if we were to take, a knife or a razor blade or something to cut out just a little section here with a little bit of width, and we'll call that little bit of width dx, since we're calling this x. And then if we were to remove that section, so take that cutout section, what we'd have is a circle with radius r and a little bit of depth dx. So our little volume, and we'll call that dv, is pi r squared, where r is a constant, it's fixed, times dx. And then what we want to do is think about adding up all of these little cuts from 0 all the way up to the top, which is delta x. So that idea of adding up a bunch of an infinite number of little cuts is the integral. So integrate pi r squared dx, where this is just a little chunk of volume from 0 to delta x, and this equals pi r squared and the x. This is just a constant. So the integral of a constant is a constant times x, and integrated from 0 to pi or delta x. So this equals pi r squared delta x, which is exactly the volume that we had up here. Only this, we derived it using integration and the idea of infinitely small cuts. So um, what we're going to be doing is thinking about volumes of cross sections. And we'll do some actual real calculation problems in a second. But let's think about, you've got some loaf of bread. And this is looking at it, from the side. It's a really nice loaf of bread. Um, this is our side view. And here's our top view. So this is like looking down on the bread, as if you're standing up on if you're like looking at the ceiling and looking down on the bread. And the idea is to find the volume of this bread, we're going to take a bunch of cross sections, each with a little bit of width dx. And the result so that's like making a little cross section here. The result, if we were to take out that little sliver, is that we're going to get something that looks kind of like that, a little piece of bread. So this is such a good example because a loaf of bread is, a sliced loaf of bread has a bunch of their uh, little volume. So each of these slices of bread provide a little bit of, um, we'll call this the area, and this our depth dx. So the volume is a times dx. And that's a little chunk of volume, so dv. And the idea is if we want to find the total volume of this bread, we have to add up all of the slices of bread. So we're going to add up each slice of bread. And notice that, as we add up the bread, um, the size of the bread piece is going to decrease a little bit. Um, So our volume of that bread loaf is just going to be the integral of all of the area cuts, and the areas are going to be changing, times dx, integrated from A to B. Okay, well, let's see that in practice. So the idea, in general, the volume of a solid between x is A and x is B that has some set cross-sectional area. It's just the area times dx. So area times dx will give us a little bit of volume from A to B. So that's going to add up all of the slices of volume. Okay, so it says find the volume of a right cylinder circular cone with base radius equals 1 and height equals 4. So the idea of this is as follows. So let's think about taking just a triangle that has a distance of 4 and this height of 1. This is a tricky topic, and I imagine that some of you are feeling a little bit um, perplexed at this point. But bear with the next couple of examples. Really try to think about what's going on. Um, so let's look at another example. Let's think about, and this is very typical to a lot of the problems that you'll be doing over the next couple days. Let's say you've got the line y equals x from, let's say, from 1 to 3. And this creates a base of a volume. So this is the, like we're standing way up on a ceiling looking down. And each cross section creates a square. So what I mean is, let's say that we take a cross section. So remember, this is a 3D shape, and we're looking down on it. So this has height coming out of the screen, coming out of the computer screen. And the idea is, if we make a cross section, and this is a little slice of bread, so we cut our slice of bread, and then we put our bread down. What we've created, where this is dx, and this is my height, so my height y. What we've created is a box, and I said that it's creating a square. So this is my y value, and the height is y. So that's the value coming out of the page. And then there's a little bit of dx. And so the area of that little dA would be y squared times dx. And not dA, that's dV. So that's my little bit of volume. This is the surface area, y times y, with a little bit of depth, dx. And so then the idea is, well, y is changing, my y value, my height, is changing as x changes. We can see that the y value gets bigger, and it's in terms of x, dx, so we need to substitute y in terms of x in here. So our dv y equals x, so we can just replace this with x squared dx. Now these terms match, and so the volume is just the sum of all those slices of bread from 1 to 3 of x squared dx. Let's look at another example. The more examples of these that we see, the better. Let's think about some function y equals x squared, and this creates a base with semi-circular cross sections. So now each slice of bread is like a semicircle. So we've got, and we're going to look from 1 to 4. Why not? So we've got our parabola. You know what a parabola looks like. And we're looking from 1 to 4. And each one of these slices, each one of our slices of bread has a little bit of width dx. And when I bring that slice of bread out, what it looks like is that, with a little bit of width there. So there's my semicircular slice of bread. And this value here is f of x. So each little area, dA, well, since it's a semicircle, it's pi r squared over 2, semicircle, times my width, dx. So we know what to do now. So we're gonna add up all of these slices of bread. So integrate from 1 to 4. I keep writing dA. That's dv. So I'm going to add up all these little chunks of volume, which are pi times f of x, where f of x is x squared. So x squared squared over 2 dx. And then let's just leave it like that, because this is the thinking, how to develop this volume. Let's look at another one more of these. And this is, I think, the hardest one for us to imagine. That's okay. So let's think about the graph y equals sine x. And y equals sine x creates a base. And we're going to have a weird bread loaf where the base for each slice is an equilateral triangle. So equilateral triangle means each side is the same. So get ready for our 30, 60, 90s to come back, which are important for trig. So we're going to look at the volume generated from x equals 0 to x equals pi. So from here all the way to here. And the idea is when we make a little slice, our slice of bread, so here's our slice of bread, and when it has a little bit of width dx, and when we pull that out, our little bit of volume is going to have this picture. Well, it's going to be an equilateral triangle where each side is f of x, and it's going to have a little bit of depth dx. So we need to think about, well, what's that area of this triangle going to be? And here's where our geometry skills are going to come in big. If we break it down like this, we know that half of the triangle, that's f of x over 2. We know that this must be 30 and 60 because it's an equilateral triangle. So this side would be f of x over 2 times root 3. So our little bit of area, the area of the whole triangle, so that's just a piece of it. That gave us the height. That gave us this. So the area of that triangle is 1/2 base times height. So this is my base. This is my height. 1/2 that area of a triangle. And so simplifying that, we have, and adding the volume piece, that a little chunk of volume is root 3 over 4 f of x squared, where f of x is sine of x. So our volume of this weird loaf of bread that's triangular and sinusoidal is the sum of all the slices from 0 to pi of root 3 over 4 times f of x, which is sine of x, squared. And there we have found the volume of our shape. Now, that concludes the topic on finding volumes of cross sections. And in the next video, same topic, we're going to look at finding volumes as we rotate shapes around an axis. This topic is significantly more challenging, I think, but that'll be up to you to decide.